not taken the other class. The first sensors we're going to look at are what we call proximity sensors. I think last class we looked at potentiometers, right? Yeah, we did potentiometers, which is a position sensor. We looked at potentiometers, we looked at absolute encoders, and we looked at incremental encoders, right? Okay. Y'all got any questions on that? Then we went over to the robot and we looked at the incremental encoder that was actually on the big FANUC robot. We like that one because it's separate. The servo motor allows you to. By the way, and that's a term I need to make sure we add. We got two types of systems that we can run. The two types of control systems that we can run, and it's not a complete system. When we run devices, we can either run them open loop or we can run them closed loop. Now, what's the difference? Anybody know? Doesn't use. It's not that it don't require, it don't use feedback. So what we do is the control circuit tells it to do it, and then it takes for granted it's done. A good example over there is on the Mitsubishi robot. There's no sensor that indicates there's a piston over there. So what will it do? Well, if there's not a piston over there, it'll swing over there, it'll drop down, it'll close its gripper, it'll come over, and there's nothing in it. It'll still run its program because it's open loop. There's no sensor out there that tells the robot controller that there is a piston over there. Okay, and there's several places that it's open loop like that. What's closed loop? It requires feedback, so it requires some type of sensor, right? You understand? Or the control system tells the actuator or tells the device to do something, and then it does what? It verifies that it's done. Now, what advantage does closed loop have? What advantage does open loop have over closed loop? A lot cheaper. So if I can do it open loop, I'm going to do it open loop because sensors cost a lot of money, right? You understand? My control system becomes more complex anytime we do closed loop. So not only do we have to put the sensor out there, but my control system has to do what? Support that sensor and decide what to do with that sensor. What advantage is closed loop? Yeah, definitely a lot more precise, because not only do we tell it what to do, we tell the motor what speed to run, but we verify it's what? Running at that speed. If it's running too slow, our control circuit would speed it up. If it's running too fast, your control circuit would slow it down, right? You understand? So if you got cruise control in your car, that's a perfect example of a closed loop system. You get up to a certain speed, you set that speed, and then you can take your foot off the gas, right? You understand? And if your engine tries to slow down, it automatically adds gas. If you speed up, it automatically takes it away. On the old systems, you actually could feel the accelerator. I don't know about the new one, but the actual accelerator pedal would actually move to set the speed. But there's limitations, right? Every closed loop system's got a limitation. So if the motor slows down and there's not enough energy from the power supply to cause it to speed up, then we get out of the limits of the control system. It's just like if you got your cruise control engaged and you go up a really, really steep hill. All right, so what happened? Well, going up a hill, it slows down, right? The car actually slows down. You can't do anything, but if you put your foot on the gas, you couldn't do any better. Right? You'll understand what I'm saying. And if you start down the hill, the car's not going to apply brakes. So once it lets the gas all the way off, and the weight of the car is causing you to get above the speed limit, above the cruise control, so you're out of the limits of the control system, right? So the first sensors is what we use in a closed loop system. And we got sensors that can sense almost anything that we as humans can almost sense, right? We can sense motion, we can sense pressure. So the first sensors that we start in, the first labs that we're actually going to do, the first lab we're going to do is a position sensor, which is the potentiometer. So that's why we got the pots over here. And if you don't have your meter in today, then you can use one of the shop meters that we have in the back. So we talked about potentiometers, and but then we have what we call limit switches. Limit switches are a proximity switch, but the limit switches have their own name, right? You understand? So normally when we use the term proximity switch, we're using it for a non-contact sensor. And a limit switch is what we call a contact sensor, right? Okay. So limit switches, we okay there? Did we cover limit switches in this class? Or was that the other class? So this is the limit switch. And what we have here, let me so here's the typical limit switch. We have all different types of what we call operators. Okay. So what happens is whatever we're trying to sense the position comes up here and hits these rollers, and you can actually hear it make. And what it does, it has a snap action like that, because we're dealing, these guys, most limit switches have that snap action like that, because when we make and break a circuit, we want to do it real fast. If we do it real slow, there's a higher probability that we'll get an arc, right? You understand? So it's got a snap action to it. Can you hear it? Now this actuates in both directions. So you have some limit switches that are only unidirectional, which means they only activate in one direction, but this guy can activate in both directions. And then we have the connection to the contact. So we'd bring our wires up through this guy, and then we would make our connection to the contacts right here. And I don't know what this has on it. It's probably at least a double pole, double throw, since it's got 4 connections on it. I would have to see. The label is gone off of it. Normally they put a label on it that tells you. In fact, here it is. Okay. So see, between 1 and 2, we have a normally closed. Between 3 and 4, we have a normally open. And we can wire it as a single pole double throw by putting a wire between 1 and 3, jump it between 1 and 3. So this is a normally open, and this right here, this is a normally closed, this is normally open. This is what we call a pilot duty, which means these guys are designed to handle a higher voltage and then a higher current. Okay, so we could use these to pick up a big relay or turn on a pretty good sized light. So these guys will run a pretty good load. So what we have is we have all types of operators. That operates these limit switches. Some of them are what we call push types, which means they literally push into the limit switch. These are rotary types, and normally the rotary types will have some type of set screw or something, so you can literally put different operators on the limit switch. Okay. So a lot of people will just carry the body, and then when you go out and replace them, you use the operator that's already on there on the one you're replacing if it's not broke. And of course, the biggest problem we have with these things is they're electromechanical devices, so something's going to fail sooner or later, but they last an extremely long time if you take care of them. Another thing we have is people don't mount them right, and they mount them too close or too far away. If they mount them too close and the actuator goes too far, you can literally break the switch, right? So I've seen these things break because people don't do what? They don't mount them right. They mount them in the wrong direction, and it only can turn this way, and then they try to turn it the other way. You'd be surprised what people do. Of course, this is the operator right here that is on the one that you got. But you got whip operators, you got roller operators, you got plunger operators, you got all different types of operators that you can buy for these limit switches. But these guys have to make physical contact contact where with the device that's trying to detect the proximity. So we have position sensors. Position sensors are going to determine the location over a range, right? You understand? A proximity sensor is going to tell us when something's at a specific spot. Okay, that makes sense. So a limit switch is a proximity switch, but they don't usually put it in that category because it's been around so long and has its own name. So normally when we talk about a proximity switch, we're talking about a non-contact sensor that tells us when something's at a certain location. And of course, we have what we call magnetic reed switches. We have wet contact, and then we have dry contact. What they do on mercury, what is mercury? It's a metal that has an extremely low melting temperature. So in ambient temperature that we occupy, the metal is already melted. And metals make really, really good conductors. Most metals make good conductors. Mercury makes a really good conductor, but it's very dangerous. So we used to use this. I was looking for my thermostat. Yeah. So this is an old thermostat, and it's using a temperature sensor that we'll talk about later on. But it's using what we call a bimetallic strip or spring. And what the bimetallic spring does is two metals that are bonded together. And metals, depending on the metals, they expand and contract with temperature at different rates. When I took a physics class, we had a light, heat, and sound physics or physical physics, and we had an expansion chamber, and we'd have these metal rods in there, and we'd put steam in there, and we had a micrometer out there so we could actually measure the expansion of different types of metals like brass and aluminum and steel. It was really neat. So you could see these metals expand at different rates. But if you put these things together, then what happens is one of them's going to expand faster. They usually put that on one side, and what does it do? It literally bends. Well, it's already bent, then it has a tendency to do what? If they put the metals on it, it has a tendency to spread out. So that's all this is right here. This is a bimetallic strip, and this used to be a thermostat. This is the way thermostats work. And what you would do is you would set a temperature over here, and then when it heated up, it would move in one direction, and when it cooled down, it would move at the other. And you can actually see the mercury in there that would fall back and make a contact. But when it made contact, it would turn your air conditioner on, right, or off, depending on what you were doing. So these were in fact, this was for heaters. It was a long time before we had central air conditioning systems. So these are the type of thermostats that we had for years. And some old houses you get into might still have one of these thermostats in there. Of course, normally the mercury is inside a glass tube. And of course, mercury is a very dangerous metal. The problem with mercury is that the molecules of mercury are literally smaller than your pores in your skin. So what does that mean? If you handle this stuff, it will absorb into your skin and get into your bloodstream. So don't ever handle mercury without any gloves or something like that. Well, it gives you mercury poison. Lead is a metal, but lead is the molecules of lead are a lot bigger than the pores in your skin. So you can handle lead without any problems, unless you've got cuts on your skin. You got to be really careful. The big problem we have with lead is people getting it in their mouth. So they'll handle lead, and then what will they do? They'll smoke a cigarette or drink a liquid or something like that. So lead, as long as you wash your hands with it, not use the sanitizer. So if you use a hand sanitizer, you're not getting rid of the lead. You're just moving it around, right? It just won't be. It would be disinfected lead, but it would be lead poisoning. So lead is predominant because for years that was the base of latex paint. That's what held the latex paint together. So latex paint was lead based. So in your old houses, you know, that's what they're talking about. Little kids will get in there and do what? Little kids eat anything. and break that lead off, and they'll stick it in the paint off, and it had a lot high contents of lead. So that's the problem with lead. But mercury, you can't even handle. You can't handle mercury in your hands like you can lead. So you can handle lead as long as you do what? Just wash your hands real good when you get to it. So this is a wet switch, wet reed switch. So usually we don't call this a reed switch. I usually refer to it as a mercury switch. For years they use it in car burglar alarm systems to determine if somebody tried to beat and break in your car. They put these things on there. If somebody tried to jack your car up and pull it off, it would trip the mercury and set off your alarm. Now they use counterweights to do that function. But this is a mercury switch. So I'll drop it, but you break it. My dad used to bring this stuff home, and we used to play with it all the time. It was so cool. Yeah, he'd bring that mercury home. They'd get until one day when my mom got in there and found some on her floor, and she reached down there and got her gold wedding band into that mercury, and it absorbed it just like that and turned it silver. So it wicked up into the gold wedding band. That was the last my dad brought mercury home. But that's back before we knew that mercury was so dangerous. The other type we have is what most people call a reed switch, but normally you say magnetic reed switch. So normally we call this guy here a mercury switch, and then most people just use this guy over here as a reed switch. Now, a reed switch works with magnetics, and I'll see if I could do this again. It worked fine when I went to another reed switch. So this is a reed switch. This is the actual switch itself. Now, usually the reed switch is encapsulated in some other material like plastic, because you can see a reed switch is made out of glass, which means if I didn't do something, this would be very fragile, right? You understand? And this is a vacuum in here. But what we have is we have two magnetic metals. So these things here, they're magnetic metals. They're ferrous metals. So see, they're attracted to magnets. And of course, what happens when we put this across a magnetic field, these contacts that are so close together, and you'll see them in here, these at the magnetic field, so we put a north on one side, we put a south on the other, and then right there where they come together, what does north and south do? They'll attract each other. So what we do is we'll put this across the magnetic field like this. Hopefully this is not the one that didn't work. It did work, though, last night. So in electronics, we use a term called continuity, and what does that mean? Now, little or no resistance, usually less than an ohm. So we use this feature. So just about all your meters have a ohm scale, and then they have a continuity scale. And normally it's got a little audio symbol on there. And what's nice about that is that we can come up here. So that means we have little or no resistance, right? You understand? Which in electronics we call it continuity, right? Okay. So what I do is we use these to trace wires all the time. We use them to check fuses, circuit breakers. So instead of me trying to look at the meter all the time, I can put a fuse across there. If it beeps, it's what? It's good. If it don't beep, it's bad. So we do that all, and I don't have to look at the meter. So right now, if this works, guys. So right now, we have what we call an open, right? You understand that? And then over here we have continuity. Y'all hear it work? Y'all heard it work? I can't hold it. I don't hear it. So when it comes close to the magnet, the switch does what? Close. When I get away from the magnet, the switch does what? Opens. So we use this guy here to sense a magnetic field. It's not solid state, If it was so, we do have a mechanical mechanism in here that could go bad, right? Anytime we have electromechanical devices, we have two things that can fail. The biggest advantage of magnetic reed switches is that they're very cheap, real cheap. So what we would do, what's in motion, we would mount the magnet on that, and then stationary, where we're trying to sense the proximity, then that's where we would actually press the reed switch. And that way we can make electrical connections to the reed switch because it's not in motion, right? You understand that? So we use these all over the place. I mean, I think I told my night class, these are the window sensors that they put on burglar alarm systems. So if you got a burglar alarm system where they come in there and they put one unit that's on your windows and the other unit that's stationary, those are going to be reed switches. Used to they have to hardwire those things, but now they actually can do. They're wireless. Most of them now are wireless, so it doesn't take real long for them to install a burglar alarm system anymore. So we have several of these on the manufacturing lines over there. To sense magnets. What they've done, and I told my night class this, is these guys are so popular now that on pneumatic cylinders are usually made out of aluminum, and aluminum is a non-ferrous metal, so it won't impede the passing of a magnetic field. So on most of our pneumatic cylinders, you can get those. So we call it a cylinder because it's usually round. And then we have a piston. And then normally we have a rod. And then we put our fluid in here, which this will be pneumatic. But the tube that this in is usually made out of aluminum. And what they'll do is they'll put a magnet back here on the piston. In fact, it usually goes in the center. And then out here, they'll mount one of those reed switches. And now what can the control system tell? Well, the control system can tell if the piston, when it's extended and when it's what? When it's retracted. And those are actually mounted on the outside of the piston. And these are usually reed switches because they're what? They're so cheap. Are we okay? They come in all sizes depending on what type of current you got. We got some, and I don't forgot what they counted. But these, what do they call that surface that all this stuff is mounted? It's got a name. With the slots in all these surfaces, these are the T-slots. These are very popular. And what they'll do is they got these little reed switches that mounts in that slot. And what you do is you slide, and if you looked at the little slot, it would have a little old tiny hook up here. And you slide the little old tiny reed switch in there, and then it's got a little old tiny set screw on one side that you do. Once you get it where you want to, you tighten that little set screw that goes out to the bottom and latches itself into the position you want to. That's what we got back here, I believe, is eighth of an inch. Little tiny things. What they'll do, though, is normally what they'll do is they'll come in and they'll put a light emitting diode in series with the switch. And these guys here don't drop very much voltage, like 1.5 volts. But good gracious, we're operating on 24 volts. So dropping 1.5 volts is basically nothing, right? You understand that? And what this means is, what will it do? Now it'll give you an indication of whether the reed switch is made or the reed switch is not made. Now on those, you got to be careful because you have to honor the polarity of the switch. So if you got a switch that's got an indicator on it, it's going to tell you where you have to put the positive, right, or where you have to put the negative. But these operate on DC. AC, you wouldn't have any problem because it's going to light up no matter, because AC constantly changes direction. It's DC where you got to be careful about the polarity on these things, if it's got an indicator light on it. And we like indicator lights Because if I don't have an indicator light, that means I got to get my dang meter out and put it across the switch and see if it makes a break. If that little light comes on, it means that switch is made. If the little light don't come on, it means the switch is not made. Which means what? I either got it out of adjustment or the switch itself is bad. Or there's an open in the circuit somewhere. Okay? Reed switches. Now, these guys are usually encapsulated inside something. So we'd have to look at them, but we'll let some of y'all go over here that's in the other class and identify what looks like reed switches. Well, but this is very, very popular. This is very, very popular in a control system that's using pneumatics. We can't do this in hydraulics. Why? Because the cylinders in hydraulics are usually made out of what? Steel. So we'd have to do it some other way. Normally what they'd do is they would mount something on the shaft. So sometimes you'll see these little cams that's mounted on the shaft, and then they'll have a limit switch on there that determines if the thing's what? Extended or retracted. So you'll see that a lot on hydraulics. Pneumatics, though, we can literally put the magnet as part of the piston itself. So all our pistons, I don't know, the majority of the pistons on the manufacturer's lines have the magnets in the piston. So I guess we could set up a lab on magnet reed switches, but we got plenty of magnets now. But I had one last night that didn't work. But the first lab that we're going to do, where we actually go over to the motor controls lab, is we're going to deal with photoelectric detectors. And photoelectric detectors, we have three main categories that we use. We have one called through the beam. And so the object, so what we do is we have a transmitter and we have a receiver. Now it's becoming very popular to put this in one unit. So we have a head, and then we'll have a unit that we attach on here, and then we run fiber optic cable out. And then we'll have the transmitter and receiver out here. And what's nice about these is you can change this head, what connects to the sensor, and you can use all three types. So the sensing head would be exactly the same. All you do is change the head that feeds the fiber optics. And also what's nice about fiber optics is your sensor is out of the way. It's not in harm's way. So it's not out there on the line. It's going to be mounted somewhere else, and you run fiber optic cable up there. Now, fiber optic cable is not, and normally what we use in industry is we use plastic. We use plastic fiber optics. So what is fiber optics? Well, it's a conductor that passes light. And you can bend it. It's the neatest stuff. I'll go get some plastic over there. And you can bend it around and stuff. As long as you don't exceed what they call the critical angle, light passes through that thing. What's that? It all depends. It depends on the core size and what type of fiber you got. So it all depends on how you go through the cladding and the thickness of the cladding. And so there's a little bit that deals with the critical angle, but that's something that's specified when you buy the conductor. Yeah, you can't. So you can't run them in loops and stuff like that. So you can't bend it a real long way, or you'll cause the light to come out the side. This works on the tendency of water. So water, anytime we try to make light pass through, two materials, if those have different indices, I forgot, refraction indices, then what would happen? So when you look at water, and if you're not looking straight down on it, if you look at water, if you ever did bow fishing, tried to fish with a bow, it's hard, because if the fish is away, the fish is not where you see it because of the bending of the light. So when it goes from air into water, they have different indices of reflection. So what would happen is it will bend the light, and you see it. It's really, really strange. So over a while, you get used to that, and you know where to aim after a lot of practice. If we get over here and get to a certain angle we call critical angle, then it'll hit the surface and bounce off. This is why when you're looking at images, that you've seen tons of pictures where the camera's back and they're taking pictures of mountains, and it looks like you got a mirror image. So we call that the critical angle. As long as you stay below the critical angle, you'll get what we call total reflection. If you exceed the critical angle, then it's going to go through the other object. So that's what we do in fiber optics. We have two types of material, like two different plastics or two different glasses, and they literally put one of the glasses in the center that we call the core, and the other glass or plastic would be that core would be embedded in the other plastic, and they're different plastics, so they have different reflections. So what happens is the light, if we don't exceed an angle, then the light would actually travel down the core. If we exceed the angle, then what will happen is it'll escape through the cladding. That makes sense? And of course, what advantage what advantage fiber in an industrial application, we're not really concerned with speed. What we're concerned with is magnetic interference. We call it EMI. So one big advantage of fiber cables, they're immune to interference. Totally immune. So you can run these things through a motor. You can run these things through a DC motor, and it wouldn't hurt them at all. You run a metal cable through a DC motor, you got problems, or you're going to have to shield the cable extremely well. So you'll put a chunk of metal around it that captures the EMI. Well, now you're dealing with cable that's very, very expensive, shielded cable, shielded metal cable or wires. So through the beam, what's going to happen? So the ones that we have on our manufacturing line uses this feature right here. But when we go to the Festo line, we'll see that all the heads are exactly the same. All the sensors are the same. It's just what they put on them, right? You understand? So they can use all three types with the same sensor, which is pretty neat. All the examples here actually use a different transmitter, and then they use a different receiver. So what we're going to do, whatever we're trying to pass through this thing, when it hits that, it does what? It blocks the beam. And now my control logic would know something's there, right? And when it moves out, then it'll be able to see that. This guy here will pick up just about anything as long as it's not what? Yeah, as long as it's not transparent. If it's transparent, these guys don't work. But even if it's translucent, it'll pick it up. Pretty neat. So these guys are used a lot. But unlike a limit switch, this device does not touch the sensor. Everybody understand that? But it's electronic. So what that means, these sensors are going to require at least 3 wires. We're going to have to put it across, and these are DC sensors. Normally your sensors, by the way, are DC. Your solid state sensors, excuse me. But they do have some AC that we'll look at. And then you have one that you'd hook your positive DC up, one you'd hook your negative DC up, and then one you'd hook your signal. Yeah, but it's still 3 wires. Eventually, they're going to have to come out. So normally what you do, most of your sensors now, they can either be hardwired, which means the wires come right out of it. The advantage of those is they're cheaper. Or you can buy them with connectors. The advantage of connectors is that if it goes bad and you need to change it, you can just take that little connector off and change the sensor out without rerunning wire. Yeah, and that's the problem. So you get to different people, and of course, you got somebody that talks about the cost, that thinks about the cost of maintaining, so they understand that they pay a little more money for the sensors with the connector so that because they know they'll save money by maintaining them. But then you got other people that say they're looking at the cost it takes to produce it, right? You understand? So both types are available. They've even got cables that have they've got cables on them that actually have LEDs on the cable connector itself, and those are really nice because what you got to understand, a lot of times you mount those sensors and you cannot see the indicator that's on the sensor, but you can see the indicator that's what on the cable. So, but the cables cost a little more money, but what does it do? It makes them cheaper to do what? Maintain. So now you don't have to get yourself to see the indicator on that. So most of your solid state sensors are going to have an indicator on the sensor itself that tells you when it picks up something, when it detects what it needs to detect, and we'll see these on our manufacturing line. Through the beam. The next we'll look at, this is the one that we're going to actually do a lab with over there. We're going to have a retro reflector. So our retro reflector looks just like this. A retro reflector is a mirrored surface, but instead of being a flat mirror, it's made up of little old tiny triangles. And what that means is that if I was to approach it from an angle, it would bounce back to whatever the transmitter is. So what's nice about a retro reflector is the light source does not have to be perfectly aligned with the reflector. If it was a mirror, then so when we shoot the beam out, so your transmitter and receiver can't be at the same spot. Well, if I shoot the beam out of this one and I used a mirror, then it would bounce back. Well, what if I didn't have the mirror at the right position? Then what would happen? It would come back and do what? We would miss it. So using mirrors are not good, but a retro reflector is going to come back to the what? To the source, which is pretty neat. Yeah, it's going to. But like the example we use is a lot of your street signs have retro reflectors on them. So if that was a mirror back there, you wouldn't see it, right? You understand, because it would reflect back the other way. But since it's a retro reflector, it bounces back to you. But it's still only good through what? To a certain distance. 4? Oh, our welders. Huh? Okay. I think it's next Friday. I hope it's next Friday. So yeah, like we said, you know, Siemens was basically European for a long time, but since Mercedes has gone to Siemens PLCs, it's really, these guys are really picking up in our service area. So we're gonna have to start teaching some of this. Y'all okay on retro reflective sensors? So this is the first one that we're gonna do. Well, that's sort of true. The sensor that we got can be used for both a retroreflective and the next one we're looking at. Which one has the ability to have the longest distance, sensing distance? Don't think so. Yeah, through retroreflective has to bounce off. So that means the light has got to travel all the way out, hit the retroreflector, and do what? Come back. Through the beam, it goes from transmitter to receiver. Well, it all depends on what type of sensor you have, whether you're using regular light or whether you're using laser for your light source. Laser has the problem we have with just about any light. If it's not a pure light, what happens as it travels over a different distance? But it diffuses what it means. So what does it do? It spreads out. So that's one advantage laser has. Laser is light at one frequency. So that means it maintains, it goes a longer distance before it diffuses. It still diffuses, but it diffuses. We used to have a laser that we used. So I could take a little laser pointer and point it back on this wall, and it would still be like this. I could take a flashlight and point it back on that wall, and it would be like that, right? You understand? We'll have to go back there and look and see what they. But the retroreflective, you just got one sensor, right? You understand? You don't have to have the transmitter and receiver. You have enough room, Jason? I like this picture better than the ones in the other slide. So you can see the way the further thing works in the retroreflector is the object we're trying to sense actually breaks the beam. Very similar principle. But the diffuse sensor is going to be, the retroreflective is going to be cheaper, right? It's only got one, even on fiber. So even if I used a common head to either do the retroreflective or sensor, fiber, we'd still have to run two fiber cables out there, right? You understand? Right? Here we wouldn't have to run any fiber at all, unless we'll see. Hold on, I'll show you all these. The last time is what we call the diffused sensor. So look what the diffuse sensor does. It literally detects light hitting the object itself. So it doesn't break the beam, it uses reflective light. So this operates opposite of a retroreflective and a thing. So this guy looks for light. The other guys look at the absence of light, right, to indicate an object is present. What would be the problem with this? Well, the amount of light you reflect back is depending on the color. Yeah. So it means the darker the object is, the less light we get back. The brighter it is, the more light we get back, which is pretty neat because what that means is I can adjust the sensitivity to ignore things. Now all these sensors are analog sensors. I'm sorry. The sensing head is analog. So the light receiver is an analog sensor. But we're going to run these into a digital device. So what does that mean? Well, that means these guys have got electronic circuits in there. So they're going to have to be powered. So it's got a single bit analog to digital converter inside of them. But it gives us the ability to set the sensitivity. So we can adjust this sensitivity to see a lot of different things, or we can adjust the sensitivity on these things to what? Only see a certain range of colors. Well, not a range. It's going to be above the set point. So we can make it ignore dark colors and see what? Light colors. Or we can adjust it so it sees the dark colors. Everybody okay? So the retroreflective is the one that we're going to do our first lab over in the lab. This is going to be the last class that we're going to have over here, by the way. After today, next week we're going to be over in A210. And why you have to have motor controls is the sensors are going to be hooked up to a motor control circuit, not a PLC. Are we okay? We don't need them for troubleshooting. We'll need them for this class, because this class we're going to be playing around with the disconnect. Probably only once, but we're going to deal with 120 volts. So all our sensors are 120 volt sensors. And that's not exactly true. Some of our sensors are 24 volt sensors. But what we'll have is we'll have a DC power supply that will plug into 124 volts, 120 volts to power the 24 volt sensor. Some of your sensors are not available. And this is what you would do in the industry. So saying you got a 24 volt sensor, all that means is that it powers up off 24 volts. Solid state sensors, by the way, DC sensors usually use a transistor as their output. But you can buy the sensors that use a relay, use a little reed relay in there. So what it does, a reed relay is pretty neat. So they'll put a reed switch in there, and then they'll wrap a magnetic coil around it. And then now you got what we call a reed relay. So if you put this in here, generates a magnetic field, what would it do? It causes a little reed switch to close. What's nice about the sensors that have these outputs is that these things will switch DC or AC. A solid state sensor, or one that has a transistor output, you can only run those things on DC. You can only switch. The signal is a DC signal. A relay output is whatever you put on there. So the Siemens PLCs have DC outputs. The Allen Bradley PLCs has relay outputs. So that means that Allen Bradley PLC, we could use the outputs on that PLC to switch either one, AC or DC. The Siemens PLCs that we have these are the ones that we bought, only will work in a DC control system, which are becoming really, really popular, by the way. And why? Yeah, they operate at 24 volts, which is well below when the safety standards really kick in. 24 volts, and it's usually DC too. And so you don't get into your higher voltages until you get into the actual big robots and stuff like that. I think our robots work. I think the big Fanuc works off like 600 volts at the robot, but it's a lot lower voltage, so they run through a transistor. It's 24 volts, and it's becoming really, really popular in new installations. You get out at an older company like, U.S. Steel, you're going to run into a lot of 120 volt stuff. Well, I'm talking about the control circuit. 240 for power, but the control circuit, the relays are usually 120 volts. So when we bought our trainers, that's what was available. So that's ours, 120 volt trainers over there. But the sensors that we're going to use are going to be, some of them are going to be 24 volt, but they're going to have relay outputs, which means they'll be able to control a 120 volt circuit. Does that make sense? Yeah, so on the Siemens, and you can get relay outputs on Siemens PLCs. It's just that the ones that they got here is in a 24 volt system, so they just bought 24 volt outputs. The Allen Bradley G1000s, I think those are 1000s or 1100s. 1000s are in the little briefcase, and those have relay outputs. And that's, and that's 120 volts on those outputs, guys. So if you're playing around with the 1100s over there, don't get around those terminal boards, because that's 120 volts. Yeah, we can take a break. This is an optical interrupter. I'll pass this around and let you look at it. So it's pretty obvious how it works. It's got an E for the emitter, and then it's got a D for the detector, and then you got to honor polarities. Can you see the little plus sign right there? Yeah, well, this would be the plus side on your signal. This would be the plus side on how you power it up. So these guys power up off DC. And it's got a photodiode in there, so you'd have to do some little math to decide what size resistor you're going to use. So if you use like a 5-volt supply, or you can use just about any DC supply, it's just that you always have to put a drop-in resistor within your emitter. You put a drop-in resistor across your detector, so you can see the output. Does that, y'all understand what I'm saying? So, so this is a optical interrupter, which is nothing but a through the beam, but it's got its own name. Don't have the circuit hooked up, guys. I should have done that, but like I said, I have absolutely no office hours this semester. I'll try to do that and bring it over to the next class. The next class from next week, we're going to be in A210. Everybody understand that? And that's where we'll do a lab today on the potentiometers, and then after that, all our labs will be on the motor controls. We have a device called, so a magnetic reed switch is a mechanical device. A Hall effect senses the magnetic field. It is an electronic circuit. So these are little Hall effect sensors right here. Hall effects sense magnetic fields. Oops. And you can see how little these things are. This is what we call a latching type. And then we have a digital type over there, which I'll hook up that to. And what we'll do is we'll see them next class. I'll have them hooked up over there so y'all can actually see these things work. But these are called Hall effect sensors. And what do they do? Notice they got 3 pins. Why do they need 3 pins? Power, common, white. 2 for power, 1 for what? Signal. So these guys sense magnetic fields. They're very similar to a magnetic reed switch. But what advantages these have? They're cheap. But the advantage, they're not as cheap as some reed switches, right? You understand that? The advantage of these guys is that they absolutely have no moving parts. So the only thing that'll fail on these things is electrically. A magnetic reed switch could either fail electrically or mechanically. Just like your car is an electromechanical device. So it senses a magnetic field. This basically shows you the way it works. That this shows 4 wires, but what you have to understand, this is minus, so what it means is these 2 wires, they share a common power supply. So that ends up with 3 wires. And these guys sense a magnetic field. Not only do they sense the magnetic field, but they can sense the strength of the field. So a magnetic reed switch, if you got enough magnetic field, it's going to close, right? But it's not actually sensing the strength. A Hall effect, we can actually use that to sense the strength of the field. So you can buy analog Hall effects, which sense the strength of the field. You can buy digital ones, which are going to look and they're going to trip at a certain threshold. Next thing we'll look at is capacitive and inductive sensors. These are solid state, which means they're not going to have any moving parts. But they might not be 3-wire sensors. They might be 2-wire sensors, and we'll explain that in a little while. No physical contact with items being checked, can be operated in a very dirty environment. Capacitive sensors can do what? They can detect solids and liquids and gases. Inductive sensors can only sense what? Metals. Well, actually, they can sense just about any metal. It's just that they get aluminum would be harder to sense than steel because steel has more. So capacitive sensors and inductive sensors look almost identical to each other. The night class, I talked about this. We have 2 types. This would be what we call an unshielded type because the sensor actually protrudes out on the end. Of the shielded site, the sensing head is actually flush with the screw. So the sensing head would be where we want the sensor to be very precise on what it picks. So if the sensing comes out like that, then this is going to generate a sensing field that looks something like that, right? Y'all understand? So it means this guy here would be able to sense objects all the way here. If it's shielded, it means, and these would be the threads right here. If it's shielded, it means the sensing head is flush with the threads that mount it. So this is going to generate a field like that. So shielded means it's more selective, right? You understand that? And it has a smaller range on what it can sense. The unshielded is less selective and it has a bigger range where it can sense. You understand that? So these are all unshielded. And we could look for shielded. So that's one of the things that you'd have to specify. A capacitive sensor works on the principle of something called capacitance. Believe it or not, AC, especially at the right frequency, thank goodness, we can do something with AC that we can't do with DC, and we can transmit AC through the air. Don't understand that. If we didn't have that ability, there would be no such thing as cell phones and radios. So what we do a capacitor basically consists of two conductors that are separated by an insulator. Now, insulators have something they call a dielectric constant. So air in a vacuum has a dielectric constant of 1. And it's a pretty good insulator. So if you got something that's got like a dielectric constant of 1.2, it means that insulator has a better insulation than what? Than air. Right, you understand that? If it's less than 1, it means it's got a less insulation of vacuum, or I'm sorry, air with moisture removed is actually what I should say. So what happens is we come up here, these are called plates, and then and we put AC on these things. If you put DC on them, they act like an open. You put AC on there, it creates an electrostatic seal through that insulator and literally passes the AC through the air. Now, to determine that, so this guy here is going to oppose AC, but what's so strange is the amount of opposition it does depends on the frequency. So if I've got a 100 ohm resistor, it's going to be 100 ohms whether you put it on AC or DC. If I've got a capacitor, if the frequency goes up, its opposition goes down. If the frequency goes down, its opposition goes up. So we don't call it resistance on a capacitor, we call it reactance. And that's the name because it reacts to frequency, right? You understand? So we don't buy capacitors in ohms. Why? Because the ohm changes with frequency. Okay, y'all understand that? Okay. So so they came up with a formula, and so X stands for reactance. And it's in ohms because it's an opposition. They say it's equal to 1 over 2 pi, so that's a constant. Normally we use 6.28 times F. What do you think F is? The frequency times C, which is the capacitance. So we buy the capacitors in a unit called capacitance, which is in units called farads. So a 100 microfarad capacitor is using microfarads and picofarads. Okay. Now, what determines the amount of capacitance is several things. Is the size of the plates. So the bigger the plates, the more capacity it has. It's just like a bucket, right? The bigger the bucket, the more capacity it has. Also, the next thing is the material the plates are made of. The third thing is the distance between the plates, and then the third is what's used as a what? Insulator. So If I have the size of the plates, the metals, and the distance, I can't do anything. But if I can come over here and do this, change the dielectric, right? You understand? Then what I do, I change the capacitance. If I change the capacitance, then I change the opposition of the capacitor. So what I did is I've created a capacitor up here. So here's my function generator. Okay, so it's generating an AC sine wave. Here it is right here. Somewhere, Rich. And then it's coming down here on one lead. And notice I have it what? Taped down. Here's my oscilloscope that's measuring it. It's taped down right here. My commons are not even connected together. They're out here in air. So I've created a capacitor. So this is a plate. This is a plate, right? You understand? And what am I using as a dielectric? I'm using what? Air. So when I come over here and look at my oscilloscope, I'm looking at one of the plates. So I am transferring this information through the air. Now notice, if I come over here and put my finger between, so I'm changing the dielectric. Can you see it go down? See it go up? What happened? My scope. The scope was still turned on. Oh, somehow I got on. So it's going to set this. Yeah, that's it. Come on. But ain't that neat? Look. Can you see it actually goes down? I mean, and if you look close enough, no matter what I put in here, whether it's plastic or whether it's metal or whatever, I change that dielectric. If I change the dielectric, then I change the amount of opposition, which means I'm either going to get more or I'm going to get what? Less. But it actually changes the amplitude of the waveform. Of course, undoubtedly I can't get the 60 cycle off of that. So that's why it's jumping, because it's picking up Alabama power. There's Alabama power right there. See the 60 cycles. We can't keep 60 cycles. 60 cycles gets in there. It's AC, right? You understand? And it's going to try to transmit through the what? Through the air. So we call this electric. We'd have to shield this a lot. I'm going to turn it up, but that's what's causing it to jump like that, is we're seeing the 60 cycles. But that's me right there. So there's a capacitive sensor, right? You understand that? And what can this thing sense? Because it's anything. If it changes the dielectric constant, which means it's changing that insulator, what I'm putting between the two leads, see, I'm not even touching them, guys. I want to show you this. I'm coming here and I'm putting my finger right here. I'm not touching either wire. But what did I just do? I changed the insulator. So now instead of being air, it's my finger, right? You understand? You can see I'm not even touching the wires. All I'm doing is just putting my finger in the center of them. Then it'll go through me. Then it'll induce in me, and I get a change. That's one of the ways we check the scope probe, is we just touch it with our finger, and you'll see 60 cycle, because it's picking up me as a capacitor, which is pretty neat. So that's my capacitor right there. So if I can take this and run it into an electronic circuit that sees that change and then triggers a digital output, then we have a capacitive sensor. But what's nice about capacitive sensors is they'll see glass. Optical sensors can't see glass. They can't see something that's transparent like gas. So capacitors can be designed to detect gas. A lot of your gas detectors that you put in your house is nothing but two plates up there, right, using air. And if gas gets up in there, it changes the dielectric. And then if it changes the dielectric, it changes the opposition. And all we have to do is come up with some type of electronic circuit that has the ability to detect that change of opposition. Of course, here we don't teach those electronics, but believe me, we have what we call comparators, that we can literally compare a set point to a back point, and if they don't compare out, it triggers a change. And those circuits are not really complicated. But the problem is we got to have AC on these things. So that means if it's a DC circuit, That means inside there we have to have an electronic circuit that we call an oscillator, right? You understand that generates an AC inside the sensor, and then we've got to have the ability to have a circuit in there that senses the change. Are we okay? That makes sense. Pretty neat. Most of these things, though, are two-wire. How can they be two-wire if they're electronic? Well, they power up through the circuit itself. So y'all have all had motor controls. So if I've got a motor control circuit and I put this capacitive sensor in there, where's my oops. I got to be running my PowerPoint, Rich. It is running somewhere. Which one is running? Right there. I can't see my marker. There it is. So in motor controls, we have what they call solid state sensors. And so you look at this, so I have this solid state sensor. Normally in motor controls, we'll put it inside a diamond shape. So if you're ever troubleshooting a motor control circuit and you see a symbol inside a diamond shape, it means it's what? Solid state. Is there current flow? Is there current flow available? So what we got to do is we got to look at this sensor like it was that, but this is a real big resistor. Let's say 1 mega ohm. Would there be current flow in the circuit? Yes or no? Yes or no, guys? Huh? Is there a complete path? Well, that's the switch. That's not the electronic circuit. So I'm putting that resistor up there to represent the electronic circuit. So this here's got ohms. It might be a couple of K ohms. This has got 1 mega ohm. So I have a circuit through the sensor power circuit like that. But it's not going to be almost no current, but they call it residual current. There's a name for it. I'd have to look it up. So we can get these capacitive sensors that are electronic and they don't have to be powered. They power up off through the circuit, right? You'll understand that. If it's a solid state sensor that needs power, then it's going to have a lead coming over here, coming out the top or the bottom that goes to power. But these sensors, these capacitive sensors and these inductive sensors are going to be two wires. They're called solid state because the circuits that generate it require so little current that they don't what? They don't run through they'll pick up through the other devices. So even if I put a contact right there, now it's not working, but as soon as that contact closes, then it's ready to work, right? So you can do ands with this thing. It's no big deal. They power up through there. So these are usually two-wire devices. And they're called solid state limit switches. And we have two types of solid state limit switches. They're either going to be what? Capacitive, or they're going to be inductive. What does capacitor sense? What can they sense? Anything. So these definitely have got a little adjustment on it to set the sensitivity, so you can decide what it senses and what it don't sense, right? But once it trips, it'll sense everything above that, right? Y'all understand that? Yes or no? This is good because these are over here. These are unshielded. And then these over here are what? Because these are flush. See this has the sensor. This is the sensing element right here. So it protrudes over the mounting threads. This right here, the sensor is flush. So they call this one where the actual sense head is flush, they call that shielded. And where it sticks out, they call it unshielded. Understand? Inductors basically are just opposite of capacitors. So inductors are nothing but loops of coils of wire. That's all they are. If we put DC on these things, they act like wire. We put AC on these things, they act like inductors. And inductors react to frequency. So that means on inductors, if the frequency goes up, the opposition goes up. If the frequency goes down, the opposition goes down. But what you do is you buy these things in something called Henrys. Now, you don't have to worry about it if you're buying an inductive sensor. I mean, you buy an inductive sensor, and the Henrys and everything are going to be built into it. But if you was to go out and buy an inductor, then you would have to know how many Henrys you wanted, right? That makes sense? So if I buy an inductive sensor, 2 pi is set. This right here is set, so the sensor operates at a certain frequency. So what is these devices varying? They're varying what? The L of the inductor. What determines the L? The number of loops. Well, the sensor, you don't control the number of loops because that's what? That's built into it. The proximity of the loops. How close are these loops together? Well, you don't control that. That's built into the what? Into the sensor. The ferrous metal the loop is coiled around. This is what determines it. So what we do is if I can get a ferrous metal into that loop or close to that loop, then we're going to change the L. If we change the L, we change the ohms. If we change the ohms, we change the output, right? Does all that make sense? I don't know if this is going to work or not. In fact, I know it's not. Oh, here's my resistor. So this is nothing but a what? But it's not wire. It's a bunch of coils of wire. Now, if I was to put DC on this, it would be a wire. And the only thing that would change would be the R of the wire, right? The length of the wire. I put AC on this, then the magnetic field on one of these coils reacts to the magnetic field on the next one, reacts to on the next one, and it causes this L right here. So I cannot measure, you cannot measure capacitance with a ohm meter. Some of your digital meters have a capacitance scale. So this one does, I think. But that's one of the things that they do now. So all your digital multimeters, are going to measure at least 3 quantities. What's the 3 things they're going to measure? Volts, ohms, amps. So it's just like a car now. So a car's got an engine, right? You understand. But what do we buy cars more for now? They're all the same. They have a gas engine or some of them's electric, but we buy cars for the look and their options, right? You understand? So that's what they do on meters now. They all measure volts, they all measure amps, and they all measure ohms. But what they've done is added more features in there. So this has got a function generator and it actually measures frequency. And then it's got a capacitance scale on here somewhere. Because here's where we hook the capacitor right here, C. Yeah, you can measure. So this generates an AC sine wave. I mean, it generates an AC wave when you hook it up there because you can't measure it without AC. So if I took a capacitor and put it across my ohm meter, it's going to measure an open, unless it's a big capacitor, and you'll actually see the plates charge up. But a small capacitor charges so fast. I'm looking for the capacitance scale. Here's logic, TTL, CMOS. Yeah, so this right here is capacitor rate. That's farads, that's not frequency. So I'd use this for capacitors. This is where I can check a transistor, which some of y'all don't look at. And then this right here is frequency right here. So this guy here has a lot of options to it. This is the meter that Lawson had before we merged. So these meters have been around for a while. But you notice it don't have a category rating on it. And so this is before 70E came out on these meters. Where do you see Cat 2 at? Oh, sorry, you're right. So this is after, so this is a Cat 2 meter. The Sperry's that we've had for so long does not have a category rating on it. Huh? Cat 2, Cat 3 is very popular on handheld meters. So usually they give you 2 ratings, and then of course they'll give you different maximum voltages for the different ratings. So you got to be careful if it's a Cat 2, Cat 3. You might have a 1,000-volt meter, but if you look at Cat 3, it might say it's rated at 600 volts, right? What did I do with my inductor? What, did they actually show it or they talk about it? Yeah. Eddie, yeah. A system went down. He went in there with his meter, put it across a 2300 volt circuit, and the meter wasn't that rated for that, and it blew up. And we got it, and they don't show the accident, but this is his coworkers. They made the video talking about Eddie and how he got into that, and it was strange. They said they saw something on fire, and they didn't realize it was a person. So it's not funny. Yeah. Said he lived for quite a while, but yeah, he didn't. Guys, what did I do with my inductor? No, I just had it in my hand. But did I pass it around? The big old loop of brown wire. Yeah, it's the loop I just showed you. Oh, here it is. No, it fell under my wheelchair. So what we're going to have to do here is we'll have to put a resistor in series with it, so I can measure the voltage drop across this. So let's see if we can do the same thing. So I'm going to disconnect my capacitor. I'm going to have to quit in a minute because I have a lap we need to do over here. And take my function generator off. And I'm going to put it across the wire. Now this is not a short circuit because now I'm putting a frequency on a coil of wire, so it's picking up what we call X sub L, right? You understand that? And then what I'm going to do, I didn't want to do it that way, Rich. You have to put the commons on a oscilloscope together. My oscilloscope went off again. My display went off. But it's not going, it's not turning off. And we'll see if this is going to work. If it's not, we won't fool around with it. These don't run off batteries. These are. No, it's not going to work. So inductive sensors sense what? Metals, right? Capacitive sensors can sense what? Yes. So let's go over to the lines and look for these sensors.